Okay, few seconds left, so I'll start. Welcome everybody. This is your first seminar of the fall series. We have three great speakers today from the Department of from our department, Dr. Jessica Ramilla, Dr. George Hutchison, and Dr. Dan Ziegler. So thank you all for coming. Enjoy the food. We have this sign-up sheet going around, so make sure you're signing up. And we'll start with our first speaker.
Thank you, Dr. Prasad. We can, hold on, I think I might be able to fix that. Okay, that's a little better, I think. All right, so I always, I was telling somebody this morning, whenever I give this lecture, I always go back and forth a bit about whether to try to deep dive into one of our subjects or cover everything in the lab. I usually choose to do the latter and try to cover everything we do, but that means that you're not going to get much depth in anything, and I'll fly through a few things, but I want to give you a feeling for what we do in our lab, which is mostly focused around diagnostic and treatment strategies for cardiovascular diseases. So we do a lot of everything, the whole spectrum, from what we call basic biology, so understanding mechanisms of how tissues form and how they become diseased, all the way through what we call very translational stuff, where we're really trying to work with clinical specimen or patients to better understand how they get disease and how we might be able to diagnose it. So everywhere in that spectrum. Probably because of my ADD, I go all over the place. So I'll start with some of the things we look at in the treatment realm. So let's start with this. So, I talk about cardiovascular disease, and the leading cause of cardiovascular disease is a heart attack, right? So you've probably heard people have a myocardial infarction or some kind of angina where blood flow is cut off from the heart and you get severe chest pain. And maybe you go to the doctor, maybe they put in a stent, or they do what we call a balloon angioplasty. They go with some kind of balloon and open that artery back up. So this usually happens when a coronary artery is blocked. It's not so dissimilar from what happens in the brain when you have a stroke. They're very similar pathologies. But that case that I just laid out for you is a best case scenario if you do have a plaque building up in your arteries. That's what we call a stable angina, and that is, again, when the doctor has time to go in, the interventional cardiologist or a cardiac surgeon can do a bypass or do the stenting. The worst case scenario is when you have one of these plaques and it ruptures. That's when you get that sudden cardiac death that can often happen due to a myocardial infarction. This plaque that's building up, that's lipid-rich, ruptures open, platelets rush in to try to stop the wound that's there, but in the end, they just completely block blood flow to the rest of your heart, and that's a worst case scenario. These are generally silent. I'll talk more about that later. But it turns out the best indicator of whether or not you're likely to have a future cardiac event, and that's very broad, is the amount of calcium mineral that you have in your arteries. So for reasons that we don't quite understand, diseased cardiovascular tissues have a propensity to basically turn to bone. So they develop this mineralization there. And this is such a good predictor that in 2018, the American Heart Association says even if you have high cholesterol, moderately high cholesterol, if you have no calcium detected in your arteries by CT scans, you don't have to go on statins. You don't have to try to lower your lipids because your risk is basically zero. And the reason we think this happens is that when that mineral forms in those arteries, you suddenly have this very, very hard tissue, this very hard mineral like bone, surrounded by otherwise soft tissue. And that causes a lot of biomechanical stress very locally. When we talk about that plaque rupture, that can exacerbate that rupture response. A lot of stress can make it more likely to rupture. Or if it becomes very hardened overall, your heart has to do a lot more work to try to push blood out into the rest of your body. So we spend a lot of time and effort trying to understand how and why that happens. So this is actually what it looks like. This is a carotid artery, so this is a CT scan from a human patient. Everything you see in white here is calcification, so that you can see how prevalent this can be, and the types of mineral that form. And if you zoom way, way, way in, you can see this mineral. So what's in orange here is that calcific mineral is not uniform. It's made up of these smaller substructures on the order of hundreds of nanometers. Okay? And I always forget to figure out how that compares to human hair. That's what people like to do. But it's smaller than a human hair. Okay? Really, really small. All right? You can't see it even by a normal microscope. These small substructures. And it turns out what those small substructures are the cells that are in these tissues release these little vesicles. You can think of them like bubbles. And those little bubbles have calcium binding proteins, and they generate free phosphate, and those are the two most important ingredients for minerals. This is what happens in the bone too. So this is some computational work trying to understand how this happens with our collaborator over in physics. But again, this is happening on the atomic scale to start building this mineral. So we take a step back and say, why did these vesicles form in the first place in these diseased tissues? And I'm not going to go through this, but we have different people working on different parts of this pathway, trying to understand how there's difference between bone and vascular minerals. So one of my students said that she hates when I do this, but Sophie, Catherine, and Mohammed, the PhD students working mostly on this project, trying to really map out this pathway. And I'll show you one, well, back up. The purpose for identifying this pathway is finding points of intervention, right? Because if we know how this works, then perhaps we can develop ways to say, can we stop this from occurring, especially in really high-risk patients. So once we identify points of intervention, then we go to mouse models in the lab, and so we often work with mice that either have chronic kidney disease, so patients with chronic kidney disease are very high risk for this happening. Or, I'll show you in a minute, we work with atherosclerotic mice, so mice that we give a high-fat diet, we basically feed them a Big Mac every day, and they get really fat, and they develop this as well. So what you're seeing here, these are aortas from mice, and so this is what a normal aorta, so the dye here is the calcium mineral, so the more yellow and white it is, the more mineral is present. This is a normal mouse, you see very little mineral. The chronic kidney disease mouse has a lot. And then we're looking at different treatments, in this case treating with EGFR inhibitor, so a growth factor receptor inhibitor, that can prevent this mineral from forming. And we like this as one of our ongoing studies in the lab because EGFR inhibitors are clinically approved for cancer therapies. And so we're looking at seeing if we can repurpose some of these inhibitors for treatment of the pathology we care about. This is some work by Anna, who's another PhD student in the lab. We're also looking at atherosclerosis. That was chronic kidney disease. That atherosclerosis is that high-fat diet-induced calcification. We have a collaboration in the College of Medicine and with the NIH that have developed not just repurposing therapeutics like I just told you, but brand new therapeutics, brand new molecules that target specific receptors that also interact with some of these pathways and may even allow us to reverse existing mineral, okay? So a big problem in cardiovascular medicine is what we call residual risk. So people aren't usually found, people don't know that they have the disease until they have chest pains, right? Some other problem. And that's a big issue because once the disease is there, once you have this mineral there, how do you get rid of it? Right? Just stopping is not enough. So even if you change your lifestyle, right? You stop smoking, you eat better, you exercise, you take cholesterol-lowering medications, sometimes your risk still remains elevated above their normal population. So it'd be better if we could return that vessel to what it's supposed to look like. And so that's the premise of some of this work. On more the engineering side, I want to bring up that these tissues in your cardiovascular system are under a tremendous amount of stress. Even more stress than a student taking senior design. Bad joke today. This is your aortic valve, or this is a model of your aortic valve. This is we did in collaboration with Dr. Ramaswamy. Your aortic valve sits between your left ventricle and your aorta. It controls blood flow out of your heart. It has to do this action 3 billion times in your life. There's very few things that we produce as humans, they can withstand 3 billion loading and unloading cycles, right? So it's remarkable in its ability to undergo this deformation. And so we also tried to understand in these tissues how their structure, so the matrix component, you heard like things like collagens and elastins, how these things come together to allow these tissues to do that, and how the cells in those tissues repair those tissues when things are going well, or how the maladaptive repair that happens when they become diseased. And so we're taking advantage of new technologies that have been developed. This is work being led by Daniel Chaparro and Peroni, with a collaboration with Dr. Lydia Koss, who was over in Biological Sciences, where we take sections of these tissues and we put them on these special slides. So what you're seeing here now, this is the aortic valve again, this is now from a mouse. These are those 3 little leaflets that were flapping in that previous video. And these special slides, each one of these dots has a unique barcode. Okay? And there you'll see the dots here. What we can do is we can use a platform developed by a company called 10x Genomics. We can tell every gene within some limit that's expressed within each one of those dots, and we can track those genes back to where they are in the tissue, right? So if we know that this particular part of the tissue has a certain amount of stress, a certain function, a certain structure, we can now say what are all the genes that are being expressed in that one little spot that might contribute to its function, or in disease might be upregulated in disease. Right? So again, from a non-biased approach to understand these pathways that are involved in maintaining the tissue. Right? And so we can do some fancy analysis to look at the aortic valve tissue, which is all in the red dots, compared to the surrounding tissue. We see that valve tissue is very special compared to, say, your left ventricle. It's different, right? A cell is not a cell, it's not a cell. Not all tissues are the same, right? And so we can start appreciating the differences in these different types of tissue. So in just a couple of minutes here, I'm going to talk to you about the other side of the lab, which is the diagnosis side. And I kind of alluded to this earlier, but the reason we care about this is most cardiovascular diseases go undiagnosed. I would guarantee you that 95% of people in this room have at least what we call fatty streaks in your arteries. Right? That seems to be just a predisposition of the human race, and also because of our Western lifestyle. But most people, so 42% of cardiovascular disease is coronary artery disease, and for most of those, the first sign is a heart attack. And 12% of those people won't survive a heart attack. Right? So you don't even know that you have it until it's too late. Right? So our goal is to develop point-of-care devices and technologies that can be used, say, at home or in a general practitioner's office to help find people who are in need of early treatment that we can then monitor and improve their lifestyle. So we're identifying a variety of different blood biomarkers that can tell you what stage you are in disease. So we're looking at how different blood biomarkers change in relation to disease. So this is a bit in the weeds, but then we take those biomarkers and we put them onto a microfluidic surface, and this is work being led by Lynn Tong in our Paths Up funded work in collaboration with Dr. Ramella. So we have different markers on these different points of this microfluidic surface, and then we look and say, okay, this marker lights up in this person's blood, they're healthy. This marker lights up, oh, there might be at early stages of cardiovascular disease. It helps us find people who we might want to then monitor more closely or give them a better workup. Right? And the idea is to make this very cheap and accessible with a cell phone-based reader that someone can maybe even do at home. I mentioned the aortic valve. The aortic valve is also very commonly diseased. It also calcifies and becomes very stiff, makes it hard for the heart to pump. And again, this is a big issue because 60% of patients in a recent study that had aortic valve disease, so they just monitored every person that came to the clinic, 60% of the patients that they found were asymptomatic, had no idea they had it, and it was fairly severe at that stage. It's very expensive once you do find it, and you have to undergo surgery or some replacement procedure to address it. So we want to also find this disease very, very early because it progresses over the course of decades. And the symptoms are, I feel a little bit tired. I'm short of breath. Okay? I feel tired every day. Right? And so you don't realize that as you progress over decades, you start feeling more tired. People say when you get the valve replacement, it's like putting on those glasses for the first time. When you didn't know you couldn't see until you put on the glasses. And now suddenly, you didn't realize how much better you feel, right? And so we're trying to enable that early. So this is what that valve looks like again. And so Valentina Dargham is leading a project where she's trying to understand if those leaflets, those little flaps starting to become diseased and start vibrating a little bit differently, can we detect that in the sounds the heart's making? That lub-dub sound that your doctor hears when he or she listens to your heart are those valve leaflets closing and vibrating. So if that structure changes a bit, perhaps we could pick that up. And so she's using digitally recorded sounds and seeing if we can use some machine learning based techniques to understand whether or not we have disease. And so we go back to our mouse model. She takes this big stethoscope and she's modified it. She puts this big stethoscope in this little mouse chest and listens to their sounds. And Dr. Danziger's helped out a lot of this as well. But she looks at those sound waves and says, using machine learning, can we correctly classify these mice as being healthy or diseased? And about 90% of the time, she does a pretty good job of that. So this is work that's also still ongoing. So you can imagine you could use this, again, in your general practitioner's office. You don't have to go to a cardiologist to find people who need further work done. So that's us. I made everyone meet yesterday to take this new picture. We make all the grad students in the back. It's a big lab. There's 9 PhD students now, and we make the undergrads sit on the floor. But it's a lot of fun to work with. If you want to learn more about us, you're welcome to follow us on social media. Footnote: the grad students run the Instagram account. I take no responsibility for that. But I'm happy to answer any questions you might have.
Do you have any available spots for undergrads?
Maybe is the answer I'll give you. So if you're interested, what I do tell folks who are interested in working, so if you're very early in the program, it's never too early to reach out, for one. At the very least, I will invite you to our lab meetings. Right? I can't promise that there's anything available. So like I said, we do have a big lab, but the first thing I do is I email the PhD students and say, do we have any prizes available? And some, it's unpredictable because we have students come and go, and sometimes things open up. But you're more than welcome to come see what we do, sit in our lab meetings, join the discussion, and then if things open up, you're welcome to join us as well.
Thank you.
What was the technology using to listen to the heart valve sounds?
Yeah, it's a digital stethoscope, and so the one we use is made by a company called Think Labs, but there's a few that are on the market now. But it's very similar to a stethoscope your doctor would use to listen to your heart, but it's just a digital version.
Any other questions? So that's just one question.
Sure.
All this, when the calcification is happening, I'm sure the blood is flowing and the shear stresses that apply that is playing a role. If we get an early detection of what's happening, is there a way to, I know everything is cascading down the line, so if you apply kind of a lowering the blood viscosity, is that a new kind of a treatment?
It might be, because the biggest problem is that rupture event, which is a combination of shear stresses, that blood stress on the arterial wall, which viscosity can play a role there, but also more of a tensile stress in the artery itself. So every time your heart beats, the artery expands, right? And so it's a combination of those two factors. And so perhaps you can play with blood properties in the meantime, lowering blood pressure, things like that. But then again, the ideal goal is to try to move that vessel back to a normal state.
Thanks. Thank you. Thanks again.
Hi everybody, I'm Zach Danziger. I'm in the neurotechnology area of the department. I think it's slightly unfair that I didn't get to go first because Dr. Hutchison does things and builds things, and I just kind of think about things. So it's possibly less exciting, but we'll see what you think. So the idea in our lab is to understand how the nervous system controls the body. The field calls this motor control. So it's a big problem. Maybe we can start by having you imagine your favorite robot. How well does the robot move? I don't know what you're thinking about. If you're thinking about a Roomba, it's not too great. If you're thinking about these machines that build cars in large factories, I'm not sure why that would be your favorite robot. But they seem to move pretty smoothly, but everything is kind of pre-programmed, right? You can't ask them to build a different kind of car. If you're thinking about transformers, okay, can't help you there, right? That's from a different world. So one of the reasons we'd like to understand how the nervous system controls the body is because there are these applications to robotics. If we understand why we are so fluid in our movement, we could build that. Or if something goes wrong in disease, we can fix it. So Parkinson's disease, or stroke, or ALS, these are all examples of diseases that affect the way the brain and nervous system moves the body. So let's start by imagining the control problem. So suppose that I would like to put my body in a new position to do something. Grab my coffee, serve a tennis ball, speak to you, right? That's all movement in my throat. If you were the brain, or if you were an engineer programming a robot, how would you do it? I wonder if you've got any ideas about this, right? So the very first thing that you might think of is, okay, I'll set a goal. I want to be in this position. And so what I will do is just look up what I need to do with my joints and muscles to put myself in that position and access that table in my brain. Let's see how that might play out. That seems like a pretty good first approximation. What could be wrong with that? Okay, so there are, let's say, 100 joints in your body that you have to actuate. And let's say that, therefore, there is about 100 muscles that you have to control for each one of those joints. Both of those are an underestimate. Then let's say every muscle can be either just on or off, right? So two states. Again, a huge underestimate. For the sake of simplicity, let's deal with a more tractable problem. So if you remember your statistics, that's a total of 2 to the power 100 possible states that you could look up in your table. Does anybody know how many particles there are in the observable universe? It is less than 2 to the power 100. Okay. So clearly we can't be storing that many action plans. So we've got to do, our brains and bodies have to do something a little smarter than that. Okay, so what's the next least complicated thing we could imagine happening? Well, what about some kind of feedback controller? We're all engineers here. So in all these engineered systems, what you end up doing is you say, I would like to be here, and then you measure where you actually are to the distance of where you want to be, and you make a small adjustment to close that gap. So this is a feedback controller. This is how the cruise control on your car works. If you say, I want to be going, what's this, Miami, right? So you want to be going 75 miles an hour, right? So then your car reads how fast your wheels are spinning. And if it's below 75, the car gives it a little bit more gas. And if it's above 75, it backs off. So you can imagine a controller that does that for a bot. I want to be here, and so if I'm over here, there's all this error in my arm, and I'll just slowly correct my muscles until I'm where I want to be. Done, right? That seems pretty good. However, science started happening, and people were testing this idea, right? Is that really enough to give everybody the richness, to give people the ability to do all of these rich movements that we see? And pretty quickly, that's inadequate. So even something like playing baseball, you have to start your movements even before you really know what's about to happen, because things are going pretty quickly. that feedback takes time. So it seems we kind of have a conscious perception that things are happening instantaneously, but everything takes time. Light's transduced in the retina, goes to the visual cortex, and then that's information's got to be sent to motor planning centers. All takes time, so that's not really fast enough. So one clever experiment that people did were have people in the lab pushing and pulling on robots. So I would ask somebody to take your arm and push the robot straight ahead. Now, what started happening was the robot was pushing back, actually pushing back to the side. So if you tried to push straight forward, what would end up happening is this, because the robot would push on you over to the side. Over about 40 attempts, people are pretty clever, so they realized that they just have to apply more force to counteract the robot and they could start reaching straight again. No problem. That could be explained by this feedback controller, right? There's error propagating, so you just update your forces to counteract that error. But then, at times unexpected to the participant, the robot would be silent. That is, it wouldn't apply that force. So what is your hypothesis, right? If we were using a feedback controller that is only responding to the errors that we saw in the movement, no problem. We would reach straight ahead because we're not making any mistakes. But what actually happened was people started moving like this, eventually counteracted the force and started moving straight. And then when the force was unexpectedly turned off, they moved like this. Okay. So this shows that we aren't using a feedback controller, we're predicting something ahead of time. So before you even started moving, before you even felt any forces, you were already pushing against what you imagined would be there. This is called a forward model of the world. So that is to say, in your mind, somehow, you are predicting what the consequences of all your actions will be before you even start moving. And then on top of that, you also have this other controller that's correcting the errors. Okay. And this is actually how a lot of modern robotics works. Now, as people, we have yet another thing going on, which is creating our own goals. This is something that robotics doesn't have very much of. And this creates another problem that requires another solution. So the forward model will tell you, given some force that I produce with my muscle, where do I think my body and the world will be after that? The feedback controller allows you to correct for errors that you see. But that doesn't answer the question, if I want my arm to be in this graceful position, what forces do I need in the first place? Okay. So all my forward model will tell me is, if I do this, then what do I expect? But not what are the commands that I need to give my muscles to do what I want. For that, you need the so-called inverse model. So for that model, you need a way, or your mind needs a way, to understand which muscle activations and forces to pick in the first place to even get you in the configuration that you want to be in. So it's these three controllers, the feedback controller, the forward model, and the inverse model, that make up a lot of our theoretical understanding about how the brain controls our body. But of course, that's not the whole story, right? Because that's just for voluntary movements. What about all the involuntary stuff? So a lot of the work that we do in our lab has to do with how the brain controls hand movements, or how you learn to do new dexterous tasks like play the guitar or learn a new interface on a computer or something. But we also think about things that are kind of involuntary. We study neural control of the lower urinary tract also. So your bladder and urethra have muscles that have to work together. to make sure you don't pee at the wrong time. You pee very efficiently when you want to, right? But the same thing that maybe you're more familiar about or you think more about, a lot of what you do with your legs is involuntary. So you certainly have voluntary control over your legs, but not completely. If you've ever stepped on a nail, what you'll notice is that you have withdrawn your foot before you felt the pain. What? So if you're doing a feedback controller, that can't possibly be working, right? So it turns out there's more than one feedback controller. It's not in your brain where you feel the pain. It's in your spinal cord. And so one of the things we've seen in the lab is that if you electrically stimulate the spinal cord, you'll get a lot of these movement patterns like the foot withdrawal reflex, even primitive walking, without having to engage the brain at all. So a lot of those patterns are stored there. And it's the same for the urinary tract. Now this is an interesting case because for the urinary tract, you kind of have voluntary control, but kind of not, right? So it's not like your arms and legs where you can do whatever you please, but it's also not like your heart where you have almost no control voluntary. It's like something in the middle. Like you can kind of decide when you're ready to go to the bathroom or when you're not, but once it's kind of happening, you don't have a lot of control over all the details, right? And so we're trying to study how these systems interact with each other, how that control is shared. Where is the control? Is it the brain, the spinal cord? So here's just one interesting problem you might think about. Suppose that you have a bit of liquid that enters your urethra. The question is, how would you want, right, if you're building this system, that's how we think about it, how would you want your system to respond? So there's a little drop of fluid that enters the urethra. What would you do?
Where is the liquid coming from?
Let's say the bladder. No. Would you tighten up the sphincter to stop the fluid? Or would you relax the sphincter? Let the fluid out?
It's a little bit just leave it as it is, no?
Do nothing, right? Yeah, right. So this is an interesting problem because if that is happening to you right now, I can tell you what you want. You want your bladder to relax, to reduce pressure, and you want your sphincter to tighten so you don't pee in your pants. Because that's kind of embarrassing. But you don't want that to happen if you're in the bathroom already. If fluid enters your urethra when you're trying to pee, the last thing you want is to tighten up your sphincter, right? You want to relax. So on top of these reflexes, there's another complicated controller that has to decide what context you're in. And some of this can be done involuntarily, like maybe you can monitor how much pressure there is in the bladder, and you assume if there's pressure in the bladder, you're trying to pee, and if not, you're not, something like this. But some of it has to also be done voluntarily, because it's those higher order cognitive centers that are determining whether or not you're in an appropriate situation to do that kind of thing. So all of these systems combine and play together, and it's our philosophy in the lab that we need to do whatever it takes to figure out how this all is working. And if we can do that, we can improve the way people learn new systems. One of the technologies we're interested in is the so-called brain-computer interface. So this is an interface that plugs directly into your brain and allows you to control some external device like a computer cursor or a prosthetic hand, very useful for someone who's paralyzed. But until we understand the mechanisms of motor learning and motor control, we don't know the best way to give people control over those systems. If we can locate some of these theoretical controllers in the actual neuroscientific substrate of the brain, we know where to put electrodes and record from for these systems. If we know how the urinary tract is controlled by the spinal cord in the brain, then when things go wrong, like spinal cord injury or when you lose bladder control when you get older, you can start building technological solutions to these things. So we're in the lab running studies on subjects, kind of torturing them like I've explained to you here. We're running animal studies on rats for the things that are too unpleasant for our human participants, and we're in the computer and on the whiteboard trying to make models of these things. So this is a general picture of the work we have going on in the lab.
Questions?
Students first.
Concerning the BCI, what's the I guess my question is why would we be interested in involuntary movements or actions? Wouldn't that be more of a somatic or voluntary response if you're controlling BCIs or looking at robotics? Like what's the main attraction for going into the involuntary aspect of robotics?
Yeah, sure. So if we want to give someone voluntary control over a system, why are we concerned with involuntary movement?
Yeah.
And the answer is we need to understand, so the way these BCIs work, or try to work, is that you plug into some area of the brain and you try to interpret what's happening there so that you can guess what the person intends to do. But until we understand how intentions are encoded in the circuitry of the brain, or what the higher level computations are about or are structured as, that's very hard to do. Because when you put your electrodes in some piece of brain tissue, the only signals you get back at you are Morse code. Okay? So it's just, you just get like 200 channels of beeps and dashes, and you don't know what those mean. So we need a theoretical framework to try to interpret what those signals could mean, right? In what context are those being used to compute something in the brain? And part of that, if you're in, let's say, an end motor area of the brain, could be involuntary, right? So you've made your plan somewhere else in the brain, and now it's coded in a motor region that's about to inform your muscles what's going on. But the voluntary planning happened somewhere else. Now we're in an involuntary region that's about to execute that plan. That's just one example.
What's the similarity between that and the forward model that you talked about earlier?
And the what, sir?
Forward model?
The forward model. Right, so that, yeah, good question. So suppose the motor-related system in the brain contains only two regions, for the sake of explanation. There's a pre-motor region where you make a plan for your action. And then there's the motor region that contains the instructions for your muscles. This is the inverse model of planning. Given my goal, what set of commands do I think I should implement? That information gets passed to the post-motor, or the motor-related region, from premotor to motor. In the motor-related region, there's your forward model. It's given the set of ideal commands, or the set of commands you'd like to, that's associated with your goal. And now you've got to issue those to the body. So that's your forward model. So what is going to happen to my body once I execute these commands?
So the forward model depends on the defined set of goals and tasks.
So one more question.
Yeah.
So in terms of evolution, you think the premotor cortex comes after the primitive walking?
Ah, interesting. Okay, so I will bracket this with saying I'm not an evolutionary biologist, but my guess would be almost certainly, yes, primitive walking would happen before. So you don't even need a brain to move. So there's a lot of animals that have very effective cyclic movement patterns with no brain at all, with no spinal cord. So almost certainly you can have very effective, especially cyclical patterns of activity with a nervous system of 300 neurons, right? You don't need this differentiation in billions of neurons.
Now, another question. Do you have available positions for undergrads?
Yeah, you should. My recommendation is to send emails to all the professors you're interested in and ask them if they will sponsor you for the CURE program, which is the undergraduate research program that BME sponsors. That's a great way to get started. And email me, email any of the professors that you're interested in, but don't do just one. Email many.
Thank you.
Yeah. While we're waiting for the
Setting up,
testimonies.
we can have a
But the question was about the forward model and spontaneity. So humans are very well known for pretty spontaneous and so let's say if for motion, for example, we said that forward model says that we're basically predicting what will happen, how we'll respond to things before we happen. So, but someone wants to disprove that you can't actually fly with a cardboard wing if you jump from the roof, and then this person breaks the leg. And then someone asks, like, well, what were you even thinking when you did that? And I said, like, I don't know. I genuinely thought that I would, like, do that. So what does this tell us about what we can learn about the prediction for robotics, for example? How can we introduce this spontaneity despite understanding the patterns and consequences?
Okay. So if you couldn't hear, the question was a little bit like, people are spontaneous and stupid, so they try something and it doesn't go how they expect. How do you work that into this framework of the forward model? Or how do you incorporate that spontaneity if you want to? So the important piece is that your forward model can be wrong, right? So model, we're taking the word model quite seriously. It is not a complete description of the external world that you have in your mind. This happens a lot when either you're trying something new and you don't have your model built up, say ice skating, or you get hurt. And what you think is going to happen when you execute some commands really doesn't, because your body has changed in some way. You don't have the muscle strength, or you don't have the balance that you used to have, right? And so this comes for free in robotics, because their forward models are always wrong, because it's very difficult to make a model that includes your body, the robot's body, and the world around you. So that can now, spontaneity is a different question. I'll leave creativity to the liberal arts.
Okay, so we can have an offline chat. I know there's more questions.
Sure.
So thanks. We'll thank the speaker.
Okay. Hi, thank you for the introduction, and thank you for being here. My name is Jessica Ranella Roman, and I'm the main PI of this laboratory called the Medical Photonics Laboratory, MPI. This is my team here below. Andres, Mel, Jenny, and Ashmal are the graduate students in the lab, and then we have many undergrads coming and going and representing us, the minions. So what we do is primarily study how light interacts with biological media for a number of diagnostic applications. Here as well, I will not go through all the projects we have in the lab, which are too many, but just to give you an overview of the primary one. So what we do is both computational work and experimental work, leaning heavily on experimental work. So we develop systems, and we also just work on a bench and try to understand phenomena better. So let me just show you a little overview of what we do. One thing that I'm working on, that I'm really committed to, is women health, because women are the ultimate underserved community. Have not been really considered in terms of diagnostic or medical intervention therapeutics up until now. It's now really starting to become a thing. There is even a femtech, a new term for technology applied to women. So I have a number of projects on women health, but this one is the one that I wanted to show you here is a new way to look at preterm labor. And particularly in all these projects, we are very much interested in a structure in the body of the woman called the cervix, which you can see up there. It's at the end of the vaginal canal, leading to the uterus. And it's the structure that allows for a baby to stay in uterus for the 9 months of gestation. But as the baby is ready to come to the world, this structure has to dissolve almost overnight, and so that so that the baby can come out with a 10 centimeter worth of head and shoulder and more through this small aperture to the world. So it's a really fantastic structure made primarily of collagen. And we study how this collagen remodels in many different ways, but primarily with light, with polarized light. And so the project that we have can be described in this little cartoon, and these are collaboration with a number of, with the medical school at University of Miami, with the Institute Polytechnique in Paris, with our funding agency, which is NSF and Stroke. In the future, hopefully, we're waiting for Congress to decide if they're going to sponsor or not our latest effort through NIH. And of course, Dr. Datzger will be part of that because he's the guru of machine learning and image analysis. So we are very hopeful that this will happen. But in the going back to the cervix, what we do is a combination, as you can see, of microscopy for animal models. So we have really high resolution microscope that are polarized, both in a linear and nonlinear regime. So we do nonlinear microscopy, linear microscopy, but always polarized. And with that, we can get a very, very accurate and very detailed overview of what happened in the cervix of the animal models. But we also build this clinical system, clinical instrument, in a point-of-care system to get an overview of the cervix of the woman, like this one on the right. So those are deployed in clinics. So these are the team that works primarily on this effort. Ajmal has done a lot of work in polarized light imaging and is now getting this fantastic data. This is one of the first time I presented on cervical remodeling, where we can see that this remodeling process is really sudden. So this is a matrix of how stiff the cervix is in the animal model. And we can see that at the early stage of pregnancy, in day 6 and 12, it's very stiff, it's very rigid, it's keeping the baby, all these babies, the mice have many babies, in uterus. But as we go to day 15 or day 18 of pregnancy, which is the later stage of pregnancy, it's remodeled, and it's almost, binary, it's also on-off. So we are exploring how that can happen, and as well as, imagine if you could do this on the other collagen in your body, like primarily in your face. How wonderful would it be that your collagen is completely, can readjust to any type of injury, like, as suddenly as the cervix does. Because after this day, as day 18, the cervix regains completely its stiffness. It's really an unbelievable structure. The other project that is going to be started very soon at the University of Miami is this portable preterm imaging system, the PRIM, which was developed by Mel. And this system is one of a kind because it's a colposcope. Usually, pretty much every woman in this room has gone for a colposcopic exam where they look at your cervix to see if you have any type of lesion, right? For pap smears or things like that. And you know that when you do that, they're going to insert a speculum. And that's the worst part of the study because the speculum is very invasive and it's kind of hurtful. So this system here, it's a speculum-free imager, speculum-free colposcope, and can be used by the user. So you can actually insert it by yourself because it uses this nice little rubbery gown, which is very soft, and I can testify to that. And you can image your cervix in the comfort of your home. So ultimately, we envision this as a point-of-care device where you are going to be able to take care of your health as a woman without having to drive, miles to your physician, wait, and then have this invasive, not so nice modality applied. So the other thing that we do is, in terms of women health, is cervical cancer. This is projects that we do primarily with collaborators in India. And so we, in a sense, we look at the same structure. We look at the cervix, but this time we look at abnormality in the epithelium and where the cancer usually starts. And we are trying to push the modality to see earlier and early stages of cervical cancer, CM1 or CM2. Microscopy, I talked to you a little bit about it, but just to say that our microscopes are super cool. They are one of a kind. They use a number of polarization strategies that are really unique in the world. And what we can do with those is, of course, we use this modality that I told you, polarization. I won't spend too much time explaining it, but we co-register with nonlinear techniques, which validate and support the data of the polarization. So once we do that, we can explore in depth what happens in tissue. This one, for example, is the retina. We can see at the very superficial stages, we can see cells, but it can also follow the polarization in the same aspect. And as we go down in the retina, we start seeing collagen structure, which are typical of the cornea. And then we can relay that information to the polarization signature. And ultimately, we can say something, as you can see here on the right, about how collagen is aligned, is structured within that tissue. That's what polarization gives you, orientation of anisotropic tissue. So switching gear a little bit, another project that we have is a collaboration with Dr. Hutchinson here, and this large group with Texas A&M, UCLA, Rice, called PATSUP. I'm the PI for PATSUP here at FIU, and it's a center sponsored by NSF, and what it does is developing technologies for underserved community, specifically for cardiovascular disease and diabetes. And so we have, an incredible variety of technology that has been developed by the entire group. But for my group specifically, and Ajmal, Mel, and Andres as well have been working on it for quite some time, is look at how obesity influences the device development. So we look at obesity because obesity is, first of all, an enormous risk factor for cardiovascular disease and diabetes. As you well know, you can see that if you are a person with obesity, your risk of cardiovascular disease skyrockets, and similarly, your risk of stroke and diabetes. But also, sadly, if we look at the statistic of the social determinant of health, so how your access to care, if you have health insurance, if you don't have a college education, or all these are determinants of health. We can see that the people that have the highest, so that they are the more poor, the one that have the less access to health and so forth, are also the one that have the highest rate of obesity and all these cardiovascular disease and diabetes. So we are, just to say that as we look at our underserved community, we have to account with the fact that many of these individuals will live with obesity. So the fact is that obesity not only, metabolically is pretty devastating, but it also changes the way your skin is composed and behaves. So at the level really of the thickness of the dermis and the perfusion within the dermis of the skin. Why this is important? It's important because it changes the way the optical property of your skin are. So the optical property of the skin are those characteristics that guide how light interacts with the skin. So if your skin is different than the skin of a Caucasian 20-year-old person that has been tested to develop this kind of devices, these wearable devices, then you will not have the same diagnostic result as this other person. So these changes can influence the diagnosis provided by wearable devices and optical devices in general. So we're interested in looking at that because we've noticed these changes, and Andres has done a fabulous work creating new models that really show how, for example, the absorption coefficient of the dermis is really different in individual with high level of obesity compared to a healthy weight individual. And this is important in devices like pulse oximeters that you use all the time, or this device again, this PPG, this device that provides heart rate. It's based on something called a photoplethysmographer, PPG, that gives you this nice signature, which we use with machine learning to get a lot of information, particularly blood pressure or things like that. So as we look at individuals that have higher and higher level of obesity, we can see that the signal changes dramatically. So you lose some of the features, the dichroic notch, and it becomes featureless. But then even more, as the individual is of different skin tone, we can see that also influences the amplitude of the signal. So for an individual that lives with obesity and has elevated skin tone, this signature becomes almost unreadable. So we are working with this group, trying to compensate for this factor. First of all, highlighting the factor because this is not well known. And so the students have done a lot of modeling of this phenomenon and look at devices like this is the Apple Watch and show that the error is, for example, the reduction in signal from an individual that has normal weight and has skin type 1, which means very, very fair skin, to an individual that has skin type 6, so it's very, very dark and high level of obesity. The reduction in signal is of 32% for the Apple Watch, for example. For Fitbit was like 60%, so it depends on your device. We're also using other modality like bioimpedance, and we're modeling bioimpedance because we think that bioimpedance could be a better way to go about measuring PPG, about measuring the pulse, rather than optical devices. We are developing optical phantoms. Optical phantoms are a system that we use to test the devices without going to an individual because they are very, very controlled. So this, for example, we're simulating here a hand with various skin levels, and we have an artery coming out, and we can reproduce the pulse within that artery, different casting methods. And then we are also developing instrument this is a collaboration with electrical engineering, and this is a system built by Andres to look at the skin of these individuals. We are about to start a large pilot study on this phenomenon, and Andres is just finishing up a manuscript showing exactly that the dermis, that what we predicted in terms of dermis changes in optical property is real, because these are experimental data that he shows, where non-obese individuals have a higher absorption coefficient in the dermis compared to the obese individual. Statistically significant. So finally, my group is in the other campus, in the Beijing campus. We can look at our website to look at all the other projects. We have a lab in HC4 where we do the microscopy, and the students are always in BH. And these are my collaborator and funding agency. Thank you.
Question? Yeah.
Has there been any response from industry to this knowledge that there is a steep curve of learning still, but they're putting this out there as though it's gonna help, but it's not really adjusted for different,
Yeah, no, there is a big response. Well, first of all, the FDA, for example, has been looking at this issue in the last few years with us. Andres, for example, has entered at the FDA and also independently, obviously. But they know that this is an issue, and they're particularly looking at skin tone, as noting that pulse oximeters don't work nearly as well in population that have elevated skin tones. So there is a whole group of people that is now really working on it and highlighting the limits of current devices and making recommendations for new devices. In terms of the big company, Apple is being sued right now for this exact issue, not for the obese yet, but for skin tone issues, and so is Fitbit. So Apple and Fitbit never claimed that their device was medical grade. It was always a toy, and it is, and that's what you really should keep in mind, that what you're given by these devices is never what your physician will tell you. Particularly in calorie counts, they're terrible calorie counts. What you think you're consuming is not nearly, it's not true, right? So just keep on walking. That's what I tell myself. Like, oh, I walked an hour, 600 calories. Yeah, let's go for a burger. No. So yes, the community is responding in different ways. Of course, we are a very litigious society, so there's a lot of lawsuits ongoing. But
Yeah. We have time.
She answered my question, I was gonna ask one.
Okay. Yeah, so if you have anything quick, we can, otherwise we can. Yeah, go ahead.
Just a quick question. Before you was talking about the cervix and looking at cancer in cervix through the optical, it is a way to like actually detect the cancer, early cancer, with your research, just with the optical, with the picture, is a way to see actually that or no?
what, to see cervical cancer?
Yeah.
Yeah. No, it's I mean, optical devices to look at cervix there are many, and they are very sensitive. The main problem with cervical cancer is capturing it at CM1 level, so at the very, very early stages, and that's where everybody is working on. So once you have the human population, the HPV virus, which pretty much we all have, the stage in between, the HPV virus and cervical cancer is called CM1, and you want to catch that change right there because there are many therapies that you can do that, many interventions that you can do, but that's very hard, and so that's where, because these are cellular level changes, and so this is where pretty much everybody is working on in the trying to push the technology to early stage, but from CM2 on, these are very usable modalities.
Let's thank the speaker again.